Okay, so welcome, and today we're going to talk about another application of in physics using integrals, which is the idea of work. Now, I'm going to start out real simple. I'm going to give you some definitions, and then we'll derive the formula, the integral that we're going to use. So now, work done by a force. So in physics, we look at work as a pusher or pull on an object. So anytime you push an object and it moves, you're doing work, okay? If it doesn't move, you're not doing any work, regardless of how strong or how much force is being applied. If the object doesn't move, work is not being done, okay? Now that could be vertical, it could be horizontal, it could be an angle, but as long as there's a force being applied to an object and the object moves, that's work. So work is force applied through a distance. And so we take that as a multiplication, so it's a force times distance is what we get for work. Now, English units for force is the pound, okay? So pounds are actually used to measure the force of gravity on an object. Pound is not the same thing as mass. In fact, in English, just so you know, in English, the unit for mass is called the slug, if I remember that right. So we measure weight in pounds, which is a force. So force in English units is pounds, distance is feet, and so work is what we call foot-pounds, okay? Now, metric system, which is the most common one that we're using in physics, is the force is going to be in kilograms, a measure of mass. Right. So the force, okay, we're using kilograms. And then distance is measured in meters. And now the work is, we use newtons. Now newtons are calculated by using kilograms times meters squared over seconds squared. So the way we get a newton, it's the amount of force, okay? 1 newton is the amount of force to move 1 kilogram at a rate of 1 meter per second squared, okay? So that's how we get this here. So we were moving 1 kilogram of mass, a meter, at a rate of 1 meter per second squared. And so that's the definition of a newton. So you'll either see newtons or you'll see foot-pounds, okay? But newtons is the most common measurement of force that we use in physics, okay? Now, in most cases, when we talk about force, we always assume a constant force, right? So in physics, if we assume a constant force, then the calculation becomes very easy. It's just work equals force times distance, right? That's up here. But very rarely do we ever get a truly constant force. Usually force is variable through a distance, right? For example, think about a spring. The amount of force that you need to compress a spring or stretch a spring depends on how far the spring is already compressed or stretched. So distance matters, right? So it depends on distance in that case. So the force required changes as you pull the spring. So we're going to deal with springs a little later, but the idea is still the same, right? Force tends to not be constant, okay? So that means we're going to have to talk about a force function, right? A force that's a function of distance, right? So we're going to have a force function, if you will, okay? So how are we going to do that? Well, let's talk about it. So now, if I have a force, and let's say a distance, right, from A to B again, let's talk about a distance from A to B, and I'm going to subdivide, right? And so let's say x of I minus 1 and x of I, right? So again, old hat, you guys are familiar with this already. You see where I'm going. So here's my little distance, okay? And what I'm going to do is, in this little subinterval, I'm going to choose my sample point, x of I. And now what I'm going to do is, on really small intervals of distance, I'm going to assume that the force is considered constant. So on a sample point, I can, say, hey, let the force be evaluated at that sample point, x of I star. Okay? So then what happens is, now on this particular subinterval, the amount of work done is f of x of I star times what? The distance traveled, right? Which in this case is x of I minus x of I minus 1. But these are regular subintervals, right? That's always the thing that we're doing, regular subintervals, which means they're the same, which we can just call them all delta x. So now, guess what? We're going to calculate work for each subinterval from A to B and add them up. So the work performed by the force over a distance is equal to the sum as I goes from 1 to n, W of I, which is going to equal the sum as I equals 1 to n of what? F of x of I star times delta x. And that is the approximation for the work done on an object from a distance A to B. Now, this is approximate. So now let's get the exact by taking the limit of this, because again, this is a Riemann sum. So n approaches infinity of the summation from I equals 1 to n of f of x star, or f of x sub I star times delta x. And guess what? Now we get the integral from A to B of f of x sub I dx. And so that becomes the integral that we're going to use to define work. So now, in the next video, I'm going to show you the theorem, and then we'll do an example. See you then.